Huh?
1, 2, 3, 4, yeah. So they're all here.
You are viewing in screen.
Person, this gentleman told me that one person probably will come late.
Okay, good. Jenkins.
कितने talking ये तो talk कर रहा है नीचे
7.
कैसे आ रही है ये वाला क्लिक होना चाहिए ये बंद होना चाहिए yes
7 and 11 and
14 and 15 are still missing. That are T. 3 people waiting room. With balls. Prince, how many do we have in the waiting room? Quite a few. Great. All right. I think that's all you have to do, Anton.
Okay, I'll be here.
Yep, exactly. If I need help, I will ask you.
Yes, okay.
Good.
And I will help you.
Yep, okay, good.
I'm gonna put that as co-host.
Yep. There's one more, yeah. Hello. Hello.
So maybe I can turn it on and it will be.
Yep.
Okay.
Sorry, what you want in your book?
Yeah. So my name, Rais. I think Sharat.
What?
Sharat, master. Sharat.
Right.
No.
Okay. This thing doesn't work. Or I'm making something wrong. Morning.
Hello, am I audible?
Yes, you are audible.
Okay, thanks. I'm calling from India, Dr. Suman Krishna Sit from Odisha Mining Corporation.
Yeah, I suppose we can start, huh? What's the time? Yeah. Let's wait a minute. Okay, let's just start. So welcome again to the Platinum Symposium. I gave a little introduction yesterday, of course, during the icebreaker, and I won't repeat everything. I just want to say that I just want to again say how glad I am that we have such a large group here. 180 people came to the symposium, so you know, as I said, I was for some time I was worried that we're not going to have a lot of people because of the pandemic and everything, and the war, and you name it. But fortunately, it seems that the people were so fed up after 3 years of virtual meetings that lots of you decided to come and meet and talk to each other and network and so on and so forth. So very important for us, for all of us, and particularly the students. So we need to try hard to engage with them and help them and outline the opportunities there are for students, PhD students, postdocs. And one of the things that we do here to help doing that is we have a student prize actually for posters and talks. Zoya Vukmanovic and Malte Junge are the little committee that will evaluate student talks and posters for the prizes, and the prizes will be announced on Friday. I think during lunchtime, perhaps we do that. So please have a look at the student posters and talks and applaud them and you know, show interest at the posters and so on and so forth. So it's very important. The other thing is I will, we made a really concerted effort here to keep the cost of the symposium as low as possible. Cardiff University helped because the lecture rooms, the facilities is all free. All I have to pay for is Leanne, the lady at registration desk, and she of course does a lot of work helping me with the financial administration and so on. But we were able to keep this at a reasonable cost, and any surplus that we have, and I think we will make a small profit, we promised that we will redistribute that to much of it to the students from developing countries, I should say, students from developing countries. So we will give you almost certainly a little contribution. We couldn't do that before the symposium. Of course, this is the problem, you know, that future organizers will also face, and past organizers. I'm sure that there are students from developing countries that don't have any money. They don't have access to funding. They would like to come, and yet we can't really, you know, help them before the symposium. We don't have income yet. And also, of course, you know, so yeah. So the other thing we are doing, and we will pass on a little surplus. Some of the surplus we have, we will pass on to the organizers of the next Platinum Symposium, so that they have a little bit of funding to help students already before the symposium and organize these things. So that's the first thing I want to say. A couple of other small things before we start in a few minutes. Poster sessions. The poster, I decided what we do is for today's poster session, which starts at 5 o'clock, 5 to whenever we finished, 5 to about, as long as you want, to 7 o'clock or so. There will be drinks and snacks. For today's poster sessions, we will only have posters on today's, you know, oil sessions. So that's chromite, layered intrusions, and GIS. So please, I already took my posters from the Wager and Brown and the chromite short course down, and the others of you who have still posters hanging up there from other sessions, please take them down. You can put them back up tomorrow or whenever your sessions are, because we may not have enough space for all posters at the same time. So please, and those of you who have posters in the chromite, layered intrusion, and GIS session, please put your posters up at tea time, so that we at lunchtime already, and then in the poster session, we can all engage with you guys and talk about your posters. So that's the posters. What else did I want to say? Rais, yesterday, not everybody, of course, was in the layered intrusion workshop, and so Rais made a little announcement, showed a slide about the 100-year Merensky Reef discovery, which will happen in South Africa next year. Apparently not in Johannesburg, somewhere hopefully in the field. A field workshop, about a week, field trips before and afterwards, a couple of days of talks. So this looks very interesting, certainly to me, and I hope to many of you too. We can ask Rais to send, if he gives me that slide, I will send it to all of you via Leanne. So that's important. Also, of course, there's the Nickel Symposium next year at Lakehead. And there is actually a little flyer here at the back of this program, although the program in being an A5, it's smaller than I thought. So it's a bit difficult to read, but I also, the flyer for the Nickel Symposium is also in an email to you guys. So please have a look at that. That's at the beginning of August. And of course, Rais's workshop is, I think, when was it, Rais? The 15th or so of August next year. So there's a week in between the Nickel Symposium and the Bushveld workshop. So, you know, please, you're all welcome to come to either of those or to both of them. I will probably go to both. So that looks very interesting. Yeah. So also special issues, of course, we have planned 2 special issues. There will be one in the Canadian Journal of Petrology and Mineralogy. Formerly Canadian mineralogist Steve Previch is in charge of that special issue. He's on the editorial board of that journal. And again, there is an announcement here and a brief explanation at the back of the program. And the second special issue will be in Mineral Deposita, more focusing on petrology and geochemistry. Whereas the Canadian mineralogy special issue, of course, is sort of more focusing on mineralogy, PGM mineralogy. So those are the 2 special issues. Please, we have already quite a number of, you know, promised submissions. So very welcome, and I would encourage you to submit to those special issues. I think that's pretty much it, actually. Just maybe one more thing. If you guys, some of you guys may want to meet with your research groups or something like that. If you want to do that, I probably can arrange a small room for you for whatever 6, 7, 8 people. If you want to do that, just let me know. I will talk to the admin people. That should not be a problem. Recordings, we will record all these sessions and send them, make them available to you guys if you want to look at them later. We have about 10 people who attend this conference virtually, so remarkably small number. Almost everybody decided to come in person, and so we will have about 10 people who attended in virtually, and I think there are about 6 talks in total who will be in virtual mode. Of course, yesterday we had already James's, and there will be another 5 or 6 across these 4 days. So that worked actually very nicely yesterday, and so the quality and everything, visual and audio quality was excellent. So you know, sometimes when you go to conferences, these sort of virtual talks, they are a bit tricky, but it seems that this is going very, very well. So I think that's pretty much it. Yep. So I'm a bit early, I guess, Rais. So that gives you an extra 5 minutes to talk about top stones and other things.
You're very impressed.
Should I start by introducing the session? Okay. So the first session of our Platinum Symposium here is on layered intrusions, and we have speakers up until just before lunch. So hopefully you will enjoy our first speaker, and this is obviously an excellent opportunity to pass anybody out that couldn't get up in the morning. Will be our keynote speaker, Rais Latypov.
Okay, good morning, everyone. First of all, I'd like to thank the organizer for inviting me to give this talk. It's really a great pleasure and honor to be the first speaker in our meeting. And today, the topic which I chosen for this talk is about the reactive porous flow. What kind of constraints we can put on this process from the Bushveld Complex, and why we care about it, because now this idea becomes increasingly more popular, both in layered intrusions, in transcrustal crystal magma, crystal marsh. So it's important to know what kind of the constraints we can get from the biggest magma chamber in the world, which is the Bushveld Complex, you know, almost 400 kilometers perhaps in diameter regionally and 9 kilometers in thickness. So apparently it may give us really idea about what was going on in the big magma chamber. And basically the question is, what was the geological state of that chamber flow cumulus in the magma which was still evolving? Simply speaking, what was the thickness of the crystal marsh? I'm not the first to address this. There were several other papers on that topic, so that I'm presenting my thoughts, or that our thoughts on this. So possible options was totally marshy, perhaps from the base to the top of the marsh, maybe partially marsh, maybe totally solid. And let's try to get these constraints from what we can see going just in the field. And I will start with the ductile brittle structures, and you already may see the spoiler at the top, which from my point of view is indicating clearly that the part of this, the rocks were totally marshy, and that's what kind of evidence. First of all, such kind of recumbent fold within non-deformed strata. You see this layer is not deformed, that is not deformed, but definitely we have a flow of the marsh and the chromite and the anophytes, so something was really causing these guys to flow, and it suggests that they were in a marshy state. We'll never say this, that's anything from just anophytes, whether there was flowing or deforming or not, unless we were lucky to have these small chromatites, which is definitely showing that there was a deformation here, was flowing. So what was marshy. And of course, we have such kind of sequine folds where both anotherite and chromatites are deformed, indicating their marshy state. We have classical bookshelf budinage. In this case, it's black, but that is orthoparxenite. That's not chromatites and shear budinage, showing that the rocks around these, surrounding this layer were in a marshy state. And that one, nice example where chromatite is broken, and apparently anotherite is just squeezed, just stuck into this fracture. And look at this nice block sitting here. Apparently it comes from that. That is the original position of the layer. It was broken and somehow was put down. Even this, it's on original position. So extensional example of extensional budinage. And that's also quite interesting example from my point of view. Again, we have this fracture in the chromatites. And if anotherite were just like that, so without chromatites, we'd never see really what's happening with anotherite. And the fact that these chromatites are deforming and deforming like that indicate that anotherite mash was kind of sucked upwards, and so they cause deformation. Perhaps there's some other interpretation which you may suggest. Of course, we're all aware of that chaotically blocks of the chromatites which are broken in anotherite, again suggesting that a marshy state of the whole sequence. But the number one for me, which I like most of all, is this one, which recently found, where we see chromatites, it's UG1 chromatites. So that is the original position of the layer. And you see how you see this tectonically broken, and they start sinking into the marshy anotherite, deforming anotherite and deforming these thin chromatites. I think beautiful examples of what is going on in this in the marsh. So preliminary conclusions from this set of observation. So definitely we have soft sediment deformation indicates that this sequence was marshy. We do have a marshy, the cumulopile was a marshy state, but the problem here is that this deformation don't give really us idea about the thickness of marsh. You can't really say how thick it was. We just have that, we just see that it was marshy, but how thick we have no idea. But all is not lost, and I'll take you to another set of observation with the planar erosional surfaces, which truncates that kind of sediments which I just showed you. And this is one of these nice outcrop against soft sediment deformation, about a kind of slumping of paraxenites. But now you see this, the upper part is planar, apparently eroded by new magma, which replenished in the chamber, and making this planar surface. And that's how it's close here. I think that we even see these remnants of these guys in this lertonite, which crystallizing on the top of the erosional surface, and we cannot, and the boundary is not really sharp in this case. You see that it's not, you cannot really put a finger there because it's gradational, and that's another just part of that. We have, that's also the recently found, that's outcrop showing melanarite, something kind of the remnant from my point of view of something much bigger. It was going like that and was again eroded away, and then on top the lane was put on top of that erosional remnant of something. Maybe that's kind of pothole, I don't know. And the final slide in this set is this one. So again, we have orthoparaxenite, we have this anotherite paraxenite pile, and where we have this nice example of soft sediment structures. You see this one, and you go this way, and as you come, you see that these find this, they are cut. And look at this boundary. It's this planar boundary going this way. And apparently there was the whole pile of this was deformed in this when it was in the marshy state and then truncated, and the new layer was put on the top of this erosional surface. That's what I see from these observations. So in this case now we see that sediments, again, these erosional sediments tell us that there was a marshy state. The pile was in a marshy state, but the fact that now we have this plain erosional surface, which usually we attribute to the new magma piles which come in and erode, we know that how much you can erode. So from field observation, we know that from field observation, we know from recent modeling we've done. So that's about 15-20 meters, which we can eat really from the top. So that tells us that if we follow this logic, of course, that tells us that this kind of structure, they should be somewhere close, not that far from the crystal liquid interface, so at least 15-20 meters maybe, maximum, which was much. So that kind of message I'm at least getting out of these outcrops. And finally, now we go to the irregular erosional surfaces. That was plain and now irregular surface, which truncates the hard rock deformation structures in a cumulative pile. And I'll show you only one example of that, which is, I think, a really beautiful example of the Merensky Reef, which that is a Merensky Reef, the black paraxenites, which was put on the crystallized on the top of the layered series, which was tilted, eroded away, and then the paraxenite of the Merensky was crystallized on top of that part. Again, logic is like that, and to have a tilting of the layered rocks without losing their coherence, it means that the state of that was not already mushy. At least maybe it was 50%, or actually maybe it's also can be hard mush. But I suspect that was much more, actually maybe 70-90, if not totally solid. That part of the intrusion, especially if you look at these when these boundaries, the knife sharp and scallop erosional surfaces, and even we cut this Oyka crease here, which is cementing the anorthosites, and I think a sequence of events here was like this. So we just formed the layering was formed first horizontally, then we tilted these without deformation, with coherence. Then we replenished the magma chamber with magma and erode these. Then we formed the deposit Merensky Reef on top of that, and then formed these pegmatitic veins. Conclusions from these parts. So from my point, the key inference from this, that floor rocks must have been almost solid, rigid, in order to for this internal layering to preserve during the tilting. So in other words, we talk about the hard rock deformation, and there's abrupt truncation of this layering, especially with this knife shaft and scallop contacts. They suggest nearly a solid state of the floor rocks. And I was thinking actually a lot about this after discussing this, and I decided to discuss it with Roberta Weiner, who recently wrote this nice review on marsh, and I'm happy to say that I got a green light from this guy that kind of behavior really indicated that's a marsh, because otherwise, if there was not marsh, but hard rocks, otherwise just magma will penetrate there and will be all kind of things which they observe in granites when there's a really they have a mushy state of the rocks. And now we'll finally go to the textural chemical observations, and some of them you've seen it in our workshop recently. I'll take you to these UG3 chromatites, below which we have mottled anorthosites, And you see that these mottles, they are usually rounded like that. And if you look at this boundary, how sharp it is, and what happens this with the paraxenites, with the oikos, it's completely truncated, and then chromatides put on top of that layering. And again, because these guys are basically oikocrest are cementing anothersites. So that tell us that that part was almost totally mashed to be truncated like that. We have interesting example of UG3 chromatides with a large OPX at the base. And interestingly enough, when we look at these images, Steve Barnes looked at this image, we found that this OPX, first of course, it's cut, and then it's used as a site for nucleation for the paraxin into the upwards into this paraxin into chromatides mash. And then even these small ones, it's still at the part of the where this nucleation can happens, and it's growing into this mashing chromatides. So again, we use these textual thing that as evidence for the hard rock, for the floor being almost hard at that time, and that's this resumed growth of truncated oikocrest. That's nicely seen in the better on that slide, I think. Then from Merensky Reef, that's an example which was shown yesterday by Steve Barnes, where you have anothersites, chromatite, and paraxenites, and just one more slide. There's anothersites, these chromatides and paraxenites, and you know the Merensky Reef is full of sulfides, and basically viscosity like they behave almost like a water. They're supposed to percolate, but in reality it doesn't happen at all. They see these red guys and the bluish, the green and the yellow one, that's all sulfides. They stop at this boundary. They cannot go further. And I think simplest implication, which we're taking from, and the inference we're taking from that's the rocks was simply solid. That's why sulfide cannot really go further at the level of erosion. And the same thing we see in the magnetite, but I think even more interesting. Look at this boundary, how it's scalloped, how it's sharp really, and that's of course that's erosion. We interpret it as erosional surfaces. And if you look closer, you see that's all what this magnetite can do. They can penetrate maybe just 1-3 millimeters into underlying anorthosite. And we would argue that that suggests that anorthosite was essentially completely solid. Otherwise, this liquid would definitely penetrate down, going and eroding the anorthosite further. If there was a grain, let's say, was marshaled, well, maybe 30–40% of the liquid, then would definitely go down. It's not the case. If you look closer at that part, you will see nicely that erosion disregards grain boundaries, and it just cuts through this polycentric twinning of the pelagic crest. So there's no, the boundary, everything is solid, and it just eroding where it's just eroding, irrespective of the grain boundaries. Another example, recent example of another side of this boundary between magnetite, that's anorthosite, where we see this boundary, this line, and basically that's virtually no magnetite below. That is where they stop. So that is where this is a distance where they can basically penetrate into anorthosite. And if we get closer view, in this case, by the way, they go through some of them at least go through the boundary, across the boundary of the plagioclase crystals, but some still doing the same thing. You see these polycentric twinning, which are eroded that with this magnetite. Another interesting feature which we found, we never seen it before, these very interesting inclusions in the plagioclase. We never have actual inclusions in the plagioclase. We have maybe interstitial magnetite, something like that, but inclusions like this, sitting just in the middle of the plagioclase crystals, we never seen before. And then we see just below the magnetite, and our preferred interpretation that is a thermochemical erosion of the plagioclase, and we just have these, and then the subsequent crystallization of magnetite in these anthracite. To conclude, to conclude, that kind of observation suggests that crystal mass in this case was just a few millimeters thick, maybe 10 millimeters thick at best, and underneath, basically we are looking at the hard rock chamber floor, totally hard chamber floor. And to conclude this part, so solid chamber floor at the level of erosion is indicated by resumed growth of truncated crystals, by termination of downward percolation of sulfide liquids in Mariansky Reef, and truncation of plagioclase grains below the magnetite. I guess each of them separately of this observation can be questioned and maybe propose some other interpretation, but I think together they give us quite solid conclusion about the state of the solid rock at the level, and I'm stressing at the level of erosion, at the level of erosion. So at Symposium we have kind of conflicting data. So we have data indicating that the cumulative pile was at the top, at least here, was mushy. And at the same time, we see evidence for the absolutely solid, almost totally solid, solid chamber floor. How to combine these observations? What we are proposing is that we propose an only uppermost portion, maybe 15-20 meters of cumulative pile of the Bushveld Complex was likely marshy, and other underlying rocks were almost totally solidified. And reactive porous flow from the topic of my presentation, and we can add here compaction, we can add soft sedimation. They will operate likely in this very thin marshy portion of the cumulative pile at the very top, and therefore cannot be responsible for any large-scale petrological feature of the Bushveld Complex. And the cumulative rock at the time, level of erosion and deposition of Mariansky Reef, chromite, and magnetite were almost entirely solid. When I say solid, I'm thinking about maybe 1-2% at best of interstitial melt. So just to visualize this, that is our idea. So totally solid cumulative pile, a few meters thick of the marshy zone, and this convecting magma melt without any crystals. And if erosion is weak and modest, then soft sediment deformation, which are developing at the top, we can see these erosional features. We can see these soft sedimentous structures at the top. And if there was no erosion, of course, the most we can see them. But if erosion is strong, then we have a chance, like for example here, if we imagine we're tilting the rocks, the uppermost part is deformed by gravity-induced flow, for example, and then we erode this part, and we may erode all these mushy part of the cumulative pile. Then the deposition of the layers, subsequent layer, will be on totally solid floor, and I think that is the case with most chromatites, magnetite, and Mariansky Reef. That is I think what is going on here. So therefore, the reactive flow, from my point of view, is likely restricted. We do have it, but it is restricted to this very thin marshy zone in the cumulative pile. And the take-home message that the marshy zone in which reactive porous flow could operate was likely not more than a few meters thick in the cumulative in the Bushveld complex. And having said that, just the last slide, it doesn't mean that reactive flow doesn't work. And I'd like to show you a recent example, I think beautiful example of that flow. It is this one, and in the sequence with Ng2 chromatites, we now start seeing these fingers which emanate from this layer upwards and eroding, it's replacing the overlying rocks, and they look like that. So basically the same thing which we see in a RAM complex, and those who will go to the field, you will see this, but it's on a small, I would say on a smaller, much smaller scale. Everything is much bigger in the Bushveld complex. And so these guys look like that. And it's another one. And it's interesting that even the chromatite seam, which is at the top, is still surviving. So we have this porous flow and reactive we are replacing, but chromatites is surviving. And I think that is example, really beautiful example of that kind of reaction in the Bushveld complex. But once again, I would argue that these are processes they're mostly working somewhere at the very top. It's not the whole whole human pile which are involved in that kind of the processes. And I think that's it from my side. Hope I was in time.
You certainly were. Thank you very much for taking to time so neatly. Are there any questions? Do we have a microphone?
Hi, thanks for your lovely talk. I was wondering about the rate dependency of processes, because when you do stuff slowly, sorry? I was wondering if you saw a role for processes depending on the rate at which they happened, because we know that things can be ductile and look much more mushy when things happen slowly. And you might see the sharper contacts when things happen quickly. Do you think there is a role for that time dependency of what you see?
We're discussing this yesterday, so that we need to move closely at these things. You know, because if you move it slowly, it will become easy to keep it will grow. That kind of things need to be we need to think of more about.
Yeah.
What is where we can find boundary between the see if it's possible at all in our rooms to get this information.
Going back to your earlier slides where you're showing all the deformation in the chromites and such here, how do you know that that's at the top of the crystal pile? Why not? What if it was happening because, say, fluids were coming up, developing at some depth within the crystal pile, and it's that zone that is now starting to form, but you're actually got a fairly sizable section above it that's actually sliding downhill.
Okay, so that's more than information which we have talked yesterday. So when you're melting and it's sliding, and that's why it's a problem.
Yeah.
I don't know.
Because we see that kind of thing in the still water. We see the same kind of deformation just below the JM reef. And I don't think it's happening at the top. I think it's happening at some depth. Yeah.
Well, you are one of the few who believes that there was kind of big much slides in such kind of improvements. So most of us will look at this. There was nothing about if Zelensky is sitting on the top of the crystal pile, and there was no kind of.
Well, I was looking at the deformations that you were showing earlier here. And the other question I have here is there any relationship of that deformation with these developing basinal and dome structures that's happened in the footwall? I think that about this time that these are forming, you're starting to get these domes in the footwall. That would cause some
I guess,
some local sloping, if you will, in the pile.
The Alan's talking about the big domes which are developing in the Bushveld Complex, kilometer size, and we do about these guys. We see such kind of. I think there was documented that we have the big deformation. I'm not sure about these ones. In the area which I'm showing, there's no domes. But it doesn't mean that it's not there, because some of them are just invisible. It's possible, yeah. So it's possible that deformation are caused by these domes. It just give us an idea what's causing this deformation.
Right, a lot of the, is it me or someone behind? Okay.
Oh, yeah, okay. Yeah. Sure.
A lot of the textures you showed looked intrusive. The cross-cutting textures. That to me looks like a large evolving body of rock that's experiencing repeated sill intrusions. The sills sometimes come into the solid bit, and then you get a very knife-sharp contact. Sometimes they intrude into mush. Sometimes they intrude into mush that's sufficiently mushy that can mingle. Sometimes there's just a little residual melt that injects as flames. You appear to have interpreted all the textures on the assumption that you have a large magma chamber. And what would they all mean if I had a large magma chamber? But they look like an evolving sill complex, what you showed.
The problem I have with these ideas, as we already discussed with you, that I really want someone to take me to the Bushveld Complex, where I'm, climbing almost on a daily basis, and took me in the field and put my fingers at Rais. That is the base of the sill. That is the top of the sills. Where are they? I don't see them. That's my big problem. I don't see the sills. For me, that's all fantasy, frankly speaking. That's all fantasy. It's nice, but we don't have full evidence for that, I'm afraid. And the petrological, arguments, which we can discuss perhaps today, so about this, the layer, the intrusion shows systematic change in crystallization sequence from base to the top, and the cryptic zonation. And to say that these systematics forms by seals, random seals, which can have a freedom to go to intrude any place in the sequence and make a mess, I'm not comfortable with this kind of idea. But I agree that that's okay, that sharp contacts can be still like, but there's other context for that.
Okay, we have two more questions over here. Just wait until the microphone comes, please.
I just have one question. It's like if the chamber flow accumulate is close to the solid, I guess the liquid, then the temperature will be below 800 or 700 Celsius. But when a new magma is flowing in, there is maybe some chilled margin, or maybe the magnetite guys, maybe the magnetite may be very small size, because there is a quick heat transfer between the magma and to the flow. But in the field trip, we also observed many large size magnetite. So can you explain this?
So I'm not entirely getting what you're saying.
I see the flow, the temperature of the magma
Yeah, they are hot.
Yeah, they are maybe below 7.
Below 7, with magma is crystallized still 1,000 degrees, something like that. So we're still talking about the hot magma.
1,000, but it maybe.
Are you saying that magma coming should be chilled again?
Yeah, the size of the magnetite at the bottom of the layer will be fine grain, not the coarse grain we observed in the field trip.
But we never see any chilling effect of new magma. So it means that, for me, it means that the magma, the rocks hot, and the magma is also hot, and it's eroding, and basically they're equilibrating, they become the same temperature.
If the flow is hot, it must be the mush, because from the thermodynamic model, it has very very small intercumulated liquid. So the system of the temperature system of the flow must be below 700 or 800.
But maybe there's a window where rocks are still hot and semi-solid, but there's no chilling.
Okay.
Do you think there's no any window? I think if we try to find
it has to be some more on this. Yeah, but I think we should have found some fine grain magnetite, or if there's a magma chamber flow.
Yeah, but with magnetite, this was